All right, in this video, what I want to do is talk a little bit more about the relationship between systems of equations and augmented matrices. So what I want to do is I want to actually forget about the process of getting a matrix into row echelon form. I want to just pretend that we're already there and then interpret. So let's say we have the matrix 1, 2, 3, 7. So 1, 2, 3, 7, 0, 1, 0, 4. And then 0, 0, 1, 0. And so I want to think about what does this mean for the solution of the underlying system. And so just when we're still getting used to these, it might be helpful to kind of still think back and kind of convert this to the systems. This is x1 plus x2, x1 plus 2x2 plus 3x3 equals 7. X2 equals 4 and x3 equals 0. So of course x2 is 4, x3 is 0. And then if we take those and plug them back into the top equation, we get the x1 plus 8 plus 0 equals 7. So that means the x1 had to be -1. So that means that our solution set, which I'm going to write as a column matrix, x1, x2, x3, is going to be -1, 4, 0. Okay, so that's how we would solve that system if we got to that row echelon form of a matrix. Next, let's solve, let's say we have 1, 0, 4, 1, 0, -4, 5, 0, 1, 2, -1, and then 0, 0, 0, 0. We have a row of zeros. Now, sometimes a row of zeros can be a problem. When it's all zeros the entire way across, it's actually okay. That's when you have two equations that are equal and then they just cancel. So in our case, this is going to reduce to x1 minus 4x3 equals 5, and x2 plus 2x3 equals -1. And what you can do is you can add the x3 terms to both sides. So that means that x1 is going to be 5 plus 4x3. x2 is going to be -1 minus 2x3. And here we could parameterize our solution set. Let's say x3 is t. And if x3 is t, that forces x1 to be 5 plus 4t. x2 would have to be -1 minus 2t. And x3 would be t. And we'd again have infinitely many solutions. Here our solution set would be a line. Okay, so that's how that would work. And then in our last example of this, I want to solve the system where we have 1, 0, 4, 7, 0, 1, 2, 3, 0, 0, 0, 4. And so let's think about what's going to happen here. And of course, we've already seen this. When you have a row of zeros in the first part of the matrix, and the constant is non-zero, then you get no solution. Because this last equation, if we were to just focus on this last equation, that says 0x1 plus 0x2 plus 0x3 equals 4. So forget about the rest of the problem. There's no solutions to this last equation. Therefore, there's no solution to the system. Okay. One thing that I should have mentioned, and I just realized I should have mentioned, is when we write our augmented matrix, like we did before. So let me just rewrite this. Even though we know that this is a nonsense system, there's no solutions, in other words. This first part, which I'm going to highlight, is yellow. So this first part is called the coefficient matrix. And this last part, after the dots, is called the constant matrix. Because that's the constant terms. right? So in the first part, you have the coefficients of the system, right? X1, X2, X3, and the last part, you have the constants. So sometimes they may refer to the coefficient matrix and the constant matrix, and that's what I'm talking about. All right. As our last item from chapter 1, and then we're actually going to move on to chapter 2. So as our last item, this is technically an application from section 1.3. There's a few other applications. I just find this one to be the most immediate and the most compelling in that way. Let's find the unique. So one thing that you know well is that between any 2 points, there's a unique line. And that's true in 2 dimensions and 3 dimensions. I'm just going to concentrate now on the 2-dimensional plane. And another thing that's true is that between any 3 points, there's at most one parabola through those 3 points. The only way that there can't be a parabola through 3 points is if they're all on the same line. So if you have 3 linear points, then there's no parabola through them. Otherwise, there's a unique parabola through any 3 points. And then there's a unique cubic equation through any 4 points. So let's try and find the unique cubic equation. By the way, a cubic equation is one, find the unique cubic, I should say, polynomial. F of x equals ax cubed plus bx squared plus cx plus d, satisfying, given any 4 points, there's at most one cubic through that. And again, you have to rule out that all the points lie on a line, any 3 points lie on a parabola. Otherwise, there's going to be a unique cubic. There might be 1 or 2 other restrictions actually, but I can't think of what they are. But anyway, so there will be at most one cubic polynomial through any 4 distinct points. And so let's say that we want the points to be, so we want our cubic polynomial to satisfy the following. We want f of 0 to be 4. We want f of 1 to be 1. F of negative 1 to be 7. And f of 2 to be 13. And so what this means, if we think about it, is that we want 4 to be equal to a times 0 cubed plus b times 0 squared plus c times 0 plus d. Okay, so we want that to be 4. We want 1, so we want our constant term to be equal to f of 1, which is a times 1 cubed plus b times 1 squared plus c times 1 plus d. We want 7 to be equal to f of negative 1. So that'll be a times negative 1 cubed plus b times negative 1 squared plus c times negative 1 plus d. And we want 13 to be f of 2. So that's going to be 8a plus 4b plus 2c plus d. And so this is going to give us a system of 4 equations and 4 unknowns. Geometry is out the window because we're talking about 4-dimensional things now. But the story is the same. We can have 0 solutions. We can have a unique solution. We can have infinitely many solutions. And those infinitely many solutions can come in a line, a plane, 3 space, or even 4 space. It's all the same equation. Sorry, no, that's not true. The infinitely many equations can be 1, 2, or 3-dimensional, not 4-dimensional. Yeah, and so what's going to happen is we have 4 equations and 4 unknowns. And so our equations are going to be, forget about the fact that this top equation is kind of silly. We're going to have 0a plus 0b plus 0c plus d equals 4. 1a plus 1b plus 1c plus 1d equals 1. Negative a plus b negative c plus d equals 7. And 8a plus 4b plus 2c plus d equals 13. And so it turns out that that's going to be our system. And whether or not we can solve the system tells us whether or not there's a unique cubic polynomial. So I should add if it exists. And I will leave that to you to figure out what are the values of A, B, C, and D that satisfy this equation if there's one at all. Okay, and so it turns out there can be, since we know that there's going to be a unique cubic polynomial, in general, we know that there can be 0, 1, or infinitely many solutions. There's not infinitely many solutions. In our case, there will be either 0 solutions or 1 solution. Okay, and again, I'll leave it to you to fill in the details, but that's everything I wanted to say about chapter 1.